This video is about calorimetry. The objective is to determine the heat change associated with combustion of fuels and solve the related problems. We will be looking at calculation based on reactions taking place in a bomb calorimeter. The equation that we are going to use is Q is equals to mc delta T, where Q is the heat change or the heat produced, and we want to calculate the amount of heat that is released using the calorimeter. M represents the mass, C the specific heat, and delta T the change in temperature. Here is a little overview of what a bomb calorimeter is. This is a generic structure to represent a bomb calorimeter setup. There are two containers, one a small one which we call the bomb calorimeter. It's usually made from steel and it has a crucible in it which can hold the fuel that we are going to perform the combustion reaction on. It can be sealed and filled with oxygen, the second reagent. Usually oxygen is taken as the excess reagent, or we add more of the oxygen. Now the fuel inside can be ignited by a small fuse, and the connection to the ignition is on the outside of the bomb calorimeter. Now once everything is set, when you ignite it, the reaction takes place, produces heat, and the heat is transferred outside. Now how do we calculate the amount of heat released? To do that, the whole bomb calorimeter is enclosed in a larger container which holds water. The quantity of water in it is measured exactly in terms of the mass of water that is used. There's a stirrer in it that stirs the water so that it can actually measure the temperature change and obtain a uniform high temperature for the final value. Now, when the temperature rises, the difference in temperature can be used to calculate the heat change. Sometimes heat change is measured at constant volume is also called internal energy. All these aspects are self-explanatory. So we're going to use the equation QV is equal to mc delta T. Certain books tend to use the letter S for representing heat capacity or specific heat capacity, and delta T is replaced by theta. What is specific heat capacity? By definition, it's the heat capacity or the amount of heat energy required to raise the temperature of 1 gram of any substance through 1 degree Celsius. So if you want to heat water, 1 gram of water to be more precise, from 0 degrees to 1 degree Celsius, how much energy is required? That quantity is what we refer to as specific heat capacity. It can be from 0 to 1 degree Celsius, or it could be from 25 to 26 degrees Celsius. The difference is 1 degree Celsius, irrespective of the temperature at which you are. Usually represented by the letter C. For water, the value of specific heat capacity is 4.18 joules per gram per degree Celsius. The unit is critical because by looking at the unit, you can actually say what that number represents. The second term that we need to be familiar with is heat capacity. We tend to use heat capacity represented by the letter capital C instead of specific heat capacity for certain reactions or certain calculations. By definition, it is the amount of heat energy required to raise the temperature of some quantity of matter through 1 degree Celsius. It can be 5 grams of water, it could be 500 grams of water. What we are trying to calculate is the total energy required for changing the temperature by 1 degree for this quantity. So typically it is specific heat capacity times the mass of the substance. Heat capacity is important to calorimeters because in a bomb calorimeter, the device has got a specific mass, usually made from a material suitable to withstand the reaction. It could be iron or steel. And therefore, instead of using the mass and the specific heat of the metal, we calculate the total heat capacity of the calorimeter as such. So it's easy for the calculation. So we tend to use heat capacities in order to determine the amount of heat energy absorbed by a calorimeter. Here is a question for you based on a bomb calorimeter. A 0.5 gram sample of naphthalene C10H8 is burned in a bomb calorimeter containing 650 grams of water at an initial temperature T1 of 20 degrees Celsius. This is the quantity of water that you have inside the bomb calorimeter, and the bomb calorimeter is immersed into this liquid. After the reaction, which is a combustion reaction, the temperature of the bomb calorimeter goes up, transfers the heat to the water. Therefore, the temperature of water rises. T2, in this case, it's going to be 26.4 degrees Celsius. The heat capacity of the calorimeter is 420 joules per degree Celsius. Now, using this data, we are supposed to calculate heat of combustion of naphthalene. Heat of combustion means how much heat energy is given out when 0.5 grams of naphthalene undergoes complete combustion. Some data needs to be given for you. Usually, this information should be provided. Specific heat capacity of water. In this case, it is 4.18 joules per gram per degree Celsius. In this case, we are trying to find out the total amount of heat energy released. So we need to know how much heat energy is absorbed by the calorimeter. Therefore, you should also be provided the heat capacity of the calorimeter, which is 420 joules per degree Celsius. Here is a solution for you. Now, in this problem, there are two separate calculations to be performed. The first one is you have to calculate the amount of heat absorbed by water, because combustion of naphthalene produces heat. Part of the heat energy is absorbed by the calorimeter and transferred to water. So we need to calculate how much heat is absorbed by water. We also need to calculate the amount of heat energy that is absorbed by the calorimeter so that we know how much energy is totally released. All of the heat energy that was produced by the combustion is now absorbed by water and the calorimeter. If you add this quantity of heat energy together, you will get the total amount of heat energy released by the combustion of 0.5 grams of naphthalene. Here is a calculation showing the amount of heat energy absorbed by water. We need to know the amount of water we have, we need to know the specific heat capacity of water, and we need to know the rise in temperature. Q, water, is equal to mc delta T. M is a mass, which is 650 grams. Specific heat capacity, C, is 4.184 joules per gram per degree Celsius. Delta T, the rise in temperature, T2 minus T1, is 6.4 degrees Celsius. Therefore, Q water is equals to product of the three numbers. That's about 17,405.44 joules. The second part of the calculation, heat absorbed by the calorimeter. Q calorimeter is equals to heat capacity of the calorimeter times rise in temperature. Like I said earlier, heat capacity means specific heat capacity times mass. So it's a single value here. Times the rise in temperature should give you the heat absorbed by the calorimeter. The specific heat capacity is unique in the sense that the value represents the energy required for 1 gram. The heat capacity gives you the amount of energy required to raise the temperature of the total mass of the calorimeter. So it's also called the calorimeter constant at times. For 20 joules per degree Celsius times 6.4 degrees will give you 2668. The units cancel out, giving you a unit of energy. So adding up equation 1 and 2, or the values from the heat energy released or absorbed by water and the calorimeter, we have a total value of 20.093 kilojoules. I have converted the joules to kilojoules by dividing the total joules by 1000. Kilo is 1000. So the total amount of energy absorbed by water and the calorimeter together is 20.093. Obviously, this amount of heat energy is coming from the calorimeter because of the combustion reaction that has taken place in it. Now that you have the value of the energy released in kilojoules, we have to convert it into kilojoules per moles. In chemistry, quantity is always represented in moles. We know 0.5 grams has released a certain quantity of heat energy. We need to know how many kilojoules would be released if you take 1 mole of naphthalene. 0.5 gram releases 20.093 kilojoules. 1 mole is 130.11 grams. Therefore, we have to calculate the amount of energy released. It's a ratio and proportion problem, or you can use dimensional analysis to come up with a final number, and the fraction for the calculation is represented in the next line. What this tells you is 20.093 kilojoules is released when 0.5 grams of naphthalene undergoes combustion. So the amount of energy released when 1 mole is used is times 130.11 gram per mole, which is the mass or the molar mass of naphthalene. Therefore, the heat of combustion of naphthalene is 5224.18 kilojoules per mole. And that is the required answer. Heat of combustion, or we can say Q, absorbed by the calorimeter and the water together is 5224.18 kilojoules. Here is a sample problem for you. Pause the video after seeing the problem, write it down, solve it, and then check the answer in the final slide. The answer to the problem is heat capacity of the calorimeter is 2243 joules per degree Celsius. So obviously in this case, you were supposed to find out the calorimetry constant, and the units kind of represent that.